This is 40 Days of Chemistry, Part 16, this time looking at 9.4.3, ion analysis and AAS. And the first thing we're going to look at is spectra. We're going to look at the AAS part of this topic first. And the first thing we need to know is that each element has a unique spectra of colours which are emitted when the atoms are heated and absorbed when light passes through its gas. And we didn't know the origin of these spectra, and the origin comes from the fact that every atom has a unique arrangement of electrons and therefore a unique arrangement of electron energies. Every atom has electrons in orbitals. We know that it goes 2 in the first, 8 in the second, 8 in the third, and so on. But every element has a unique energy for these orbitals, and therefore it takes unique energy for electrons to jump between these orbitals. So for example, when an atom is heated, the heat energy is absorbed by the electrons, causing the inner shell electrons to jump up to the outer shells. When the atom cools down again, the electrons jump back to the lower shells, and by jumping back they're going from a high energy orbital to a low energy orbital, and they've got to give off energy exactly equal to their energy jump. And the energy they give off is light, and every colour of light has a unique energy, and therefore when the electrons jump down they give off unique colours of light, or unique energies of light. Hence we get this thing called the emission spectrum, these unique colours of light emitted by an atom when you heat it up, and then it cools down, electrons jump back to the ground state. By the same token, if instead of heating, if we shine light through gaseous atoms, they're not bound to any other atoms, there's no bonding going on, there's just single atoms. If we shine light into this atom, the only colours of light the atom can absorb are the colours that exactly correspond to an electron jump. So for example, when electrons were being heated and cooling down, the jumps were equivalent to blue light, yellow light and orange light, and therefore when we shine light through this atom, the only colours of light it can absorb are the energies or the colours of light corresponding to those same three jumps. So when the light shines through, only the orange, yellow and blue are absorbed, all the other lights get through. And that's where we get the what's called the absorption spectrum, the exact colours of light absorbed by atoms. And as you can see, the emission and absorption spectrum exactly correspond because it's to do with the energy levels of the electrons. But just be aware that depending on how many atoms you've got in the way, and depending on how bright the light source is, it will absorb some orange, yellow and blue light, but it won't absorb it all depending on how much light you've got and how many atoms you've got. And that's going to be very important when we think about how we're going to do an AAS analysis. And these diagrams are just down here to remind you again that light is absorbed or any form of energy is absorbed to make electrons jump up orbitals, but when electrons jump down orbitals, they only give off a light. And that leads to the AAS process, atomic absorption spectroscopy. The whole point of AAS is to analyze the concentration of a metal ion, and please make note it's for metals, it's not for non-metals, it's for analyzing concentration of metals, is to analyze the concentration of metal ions in a solution to very high accuracy, down to parts per billion, ppb. So how do we do it? Well, the first thing we do is we choose a lamp that contains the metal that we're testing for, because when we heat that metal up inside that lamp, it's going to give off those unique colours of light which are absorbed by the metal we're testing for. And before we do any testing, the first thing we do is pass that light through the AAS machine where there's no sample there at all. So all the light's coming out of our lamp, it's going through the furnace has no sample inside there, it then goes from the furnace to the monochromator. The monochromator just chooses one colour of light only, which increases accuracy of analysis. That then passes to the photomultiplier, which increases the electronic signal. It doesn't actually make the intensity of light brighter as I've shown here, it just makes the electronic signal stronger. And we get what's called the I0, or original intensity reading. That's the intensity of that colour of light that gets through the AAS machine when there's no sample there. Then we actually put the sample inside the AAS machine. What we do is we have a furnace here, and we have the sample is basically sucked up or turned into an aerosol or aspirated inside the furnace. The furnace is there to make sure it's completely vaporized, so the sample has only got atoms. There's a whole lot of atoms floating around in here, and assumingly there'll be some of the atoms we're testing for inside this sample. So the light's going to come from our lamp, which contains the metal being tested, so it's only producing these colours of light which will be absorbed. That light then passes to the sample. If there are some atoms that we're looking for inside that, they'll absorb some of that light, and therefore there'll be less intense light coming out because some of that light's been absorbed by our sample. It then passes through the monochromator to choose one wavelength of light only to increase the accuracy of analysis. It passes through the photomultiplier to increase the signal intensity, once again to increase the accuracy of analysis. And we can record now the intensity of light that got through the AAS machine when there was the sample there. And obviously it's going to be less intense than it was when there was no sample there. And obviously if we increase the concentration of the atoms in the sample we're looking at, we're going to increase the absorbance. So clearly if there's more atoms in the sample, there'll be less light getting through. If there's less of those atoms we're testing for in the sample, there'll be more light getting through. And in actual fact, the percent absorption of light is directly proportional to the concentration of our sample in parts per million. This mathematics here is interesting if you're curious how it works, but this is the key relationship you've got to know. The percent absorption of light is directly proportional to the concentration of our sample in parts per million, and that's how AAS works. But to figure out the concentration of an unknown sample, the first thing you got to do is make up what's called a calibration curve. And our calibration curve, we make up a series of standard solutions of known concentration, in this case copper, and we measure their absorbance inside the AAS machine. So for example, 0.77 means 77% absorption. We then plot absorbance versus the concentration in parts per million, and we get this line here which is drawn in blue, the blue dots and the blue line, and that's called our calibration curve. Then we can get our unknown samples. We can put our unknown samples in the AAS machine. We don't know their concentration. We can measure their absorbance though, and by measuring their absorbance, and don't forget to put these lines in the HSC, it's very important. This first sample had an absorbance of 0.44. We draw across to our line of best fit and then down again, and that means this first sample had about 13 parts per million copper inside. The next sample had a 0.9 absorbance. We can draw that across here. It had about a 25.5 parts per million concentration. But this is a very interesting question because it asks us to assess the validity of both answers. So assess means positive and negative in judgment. Well, as we know, AAS is a very accurate technique and very reliable and a valid technique to measure concentrations. However, this first sample with 0.44 absorbance was inside the range of our testing. Our standard solutions went from 0 to 0.77 absorbance, and they went from 0 to 25 parts per million. So this 0.4 absorbance and 13 parts per million was in the range of our calibration curve. To calculate this 0.9's concentration, it was outside the range of our calibration curve. So what we say is for the 0.4 absorbance sample, that data was interpolated inside our results, whereas the 0.9 sample was extrapolated outside our results, and therefore this answer here for the 0.44 was more valid or more accurate than for the 0.9 because we didn't have to extrapolate. But just in general, the general advantages of AES, the thing you must say, it's accurate. It's accurate to parts per billion, which before this we couldn't get that accurate as far as analysis is concerned. Compared to previous techniques and other techniques, it's also much faster, especially if you're testing for one metal only. But it is expensive, and if you're testing for more than one metal, you've got to change the lamp and make a new calibration curve for every metal you're testing. So why is that important? Why is AES important when we're testing for heavy metals? Well, the definition of a heavy metal is fairly loose. There is no strict definition of a heavy metal. It's basically just a heavy transition metal which causes toxic effects. And the example we looked at was lead. Lead has no biological function. There's no safe lower limit. It's harmful in all concentrations. It's a neurotoxin. It affects your circulatory system and also causes reproductive harm. The main reasons it's found in the environment is because of leaded paint and also leaded petrol. Therefore, it's common in air and soil and dust. The main sources these days, particularly seeing that leaded paint and leaded petrol are being banned, you still find it in solder and you still find it in car batteries. So a lot of it's in automotive and e-waste, so therefore can be leached from rubbish tips. It's also a major contributor to the atmosphere by lead smelting. And we look here at this chart. You can see here at 1.5 parts per million it's actually fatal, and all these effects here happen at less than 1.5 parts per million, and therefore you need something like AES to analyse it properly. So AES is ideal because it's accurate to low concentrations where lead can cause harmful effects. You can use AES to analyse air, soil and blood samples, and the example case study we looked at was in Port Pirie, the world's largest lead smelter in South Australia. It's the world's largest lead smelter. They had to do blood sampling of children there, and they found that around the smelter there was particularly high lead levels, and therefore they've had to take action to do something about that. And so therefore we monitor lead by AES so we can take action if there is a problem, and also review our treatment strategies as well. The next thing we looked at was for trace elements. Now a trace element is an element that's less than 100 parts per million. That's just in pure chemistry. In biology though, it's an element that's needed in a very tiny amounts for proper functioning of the body. And we looked at the fact that in Western Australia there was cobalt deficiency in the soil, which meant that sheep couldn't grow properly. There was one case in Victoria where there was molybdenum deficiency in the soil, therefore legumes couldn't grow properly. And the main idea is that before AES, little was known about trace elements because we couldn't measure things in such low concentrations. But now we've got AES, we can actually analyse soils, and if we do find a deficiency, action can be taken. So for example, we can use either cobalt or molybdenum-rich soils to do something about it. So AS is very important for monitoring what chemicals are there, and then also monitoring have our solution techniques worked. So what was used before AS analysis? Well, we did study this as well. We studied what's called precipitation analysis, or wet chemistry, actually mixing chemicals together to cause chemical reactions to take place, so we could figure out what unknown chemicals are in a sample. And they can be qualitative, which means what elements are present in the sample, or they could be quantitative, and in our case we did gravimetric analysis. We actually weighed the precipitates we produced to do calculations to determine the concentration of sample. For ion analysis though, the first time when we did the qualitative one, the logic of our analysis was we wanted to use the minimum number of steps to minimize use of chemicals. We wanted to make sure every step was safe to ensure safety. We wanted to make sure that every step served a purpose, so every step distinguished between ions, and probably the key one, that no two ions gave identical results, so there was no ambiguity in our answers. And it's very important for that we actually add chemicals in the right order, hence we made our flowcharts. So for example, if we were testing for anions, if we were testing for chloride, sulfate and carbonate to see if any of those ions were there, and we chose to add lead first, and we got a white precipitate, that wouldn't tell us very much, because lead chloride, lead carbonate and lead sulfate are all white precipitates, and therefore by getting a white precipitate we haven't actually identified which anion is there. So choosing which chemical you add first, second and third, hence our flowcharts, is very important. For anion testing for the HSC, we have to be able to distinguish between chloride, phosphate, carbonate and sulfate. And the logic we chose was this. First of all, we add nitric acid. The nitrate was not going to affect our results in any way, but by adding nitric acid makes the solution acidic. If there's any carbonate in there, it'll react with the nitric acid, therefore producing bubbles. So that's our first way of analysing what chemicals are there. Also, if we made it acidic, that's going to help with our future analysis. The next thing we're going to do, we've got an acidic solution now. It may have chloride, phosphate or sulfate in it. If we add barium and we get a white precipitate, that must have been barium sulfate. Phosphate and sulfate will both precipitate with barium, or both want to precipitate with barium, but phosphate can't precipitate in the acidic solution. So the only one that could precipitate with barium in this situation is the sulfate. But now we've got an acidic solution which does contain barium ions, and it could contain chloride or phosphate. So what we can do now is we can add ammonia. By adding the ammonia, we're stopping the solution being acidic because ammonia is a base. We're neutralizing the solution. And if we add ammonia and all of a sudden a white precipitate appears, that means there must have been phosphate in there all along. Because the phosphate won't react with the nitric acid, it won't react with the barium in acidic conditions, but as soon as you make it neutral, if there's any phosphate there, then it will react with the barium. So if we get a white precipitate at this stage, but after adding the ammonia to neutralize it, that must have been phosphate all along. The next step, we add silver ions, because if there's any chloride ions in there, they wouldn't have reacted with nitric acid or barium, but if we add silver ions there and it forms a white precipitate which turns dark in the sunlight, that must have been chloride ions in the solution. If we don't get any bubbles, don't get any white precipitate or any white precipitate that turns black, there might have been nitrate ions or something in there, but that's how we do our anion testing. Our cation testing flowchart, we have to distinguish between a lot more different cations: lead, copper, calcium, barium, iron 2+ and iron 3+ ions. And the first step we did is we added chloride, because lead is the only species there that reacts with chloride. So if we get a white precipitate there, it must have been lead chloride. One of the common things we add to test for lead though, or something you can confirm, is by adding iodide ions. If it turns bright yellow, it must have been lead in the solution. But if we got no precipitate in that first test, that still leaves 5 different possible ions that could be there. So the next thing we do is we add sulfate ions. Now the bad thing about this, even though it does distinguish, is we do get 2 possible precipitates. If we get a white precipitate there, it could be barium ions or it could be calcium ions. But the reason why that's okay is because we can do the flame test on those chemicals, because we know that calcium produces a brick red flame and barium produces an apple green flame. So if we do get a white precipitate here, all we've got to do is the flame test to distinguish between the barium ions and the calcium ions. But if we get no precipitate, that means we can still have copper, iron 2+ or iron 3+. And the next thing we do is add hydroxide ions, hence sodium hydroxide or potassium hydroxide, something like that. Now all 3 of these will precipitate with hydroxide, but the reason why that's okay is they form distinctly coloured samples. Copper forms a blue precipitate. Iron 2+ forms a green precipitate, and iron 3+ forms a brown precipitate, and therefore by looking at the colour of those precipitates we can easily see what ion was there. The last thing we did in 9.4.3 was our quantitative ion testing in terms of our gravimetric analysis. Gravimetric analysis just means using mass measurements or weight measurements to determine concentration. And what our purpose of our experiment was to do a sulfate in a fertilizer. What's the weight percent sulfate in a fertilizer? And what I've done is written down the key steps of the method that relate to the accuracy in gravimetric analysis, and I've used a color code here. The red steps were to avoid overestimates, and the blue steps were to avoid underestimates. So the first thing we did was we made a standard solution of the fertilizer by dissolving in nitric acid. And the point of dissolving in nitric acid was, well, it helped to dissolve, but it will dissolve any carbonates, and any phosphates there won't precipitate in acidic conditions. So it's going to help us later on. That means only sulfates can precipitate, nothing else will precipitate. Because what we're adding is adding barium. And if there were any carbonates and phosphates in our solution, barium would precipitate with them as well, therefore producing barium carbonate, barium phosphate, and barium sulfate. When we weighed it, we weigh them all together, and we'd be thinking they're sulfate when they're not. So adding nitric acid, the carbonates dissolve and bubble out of solution, the phosphates can't precipitate with barium, and therefore we can only precipitate the sulfate. The next step we did was we added excess barium chloride to the sample. How do we know we added excess? We kept on adding to the number of precipitate formed. That ensures that all the sulfates precipitated. If we didn't add excess barium chloride, we might not produce enough precipitate and therefore get an underestimate. The next thing we do is we filter that precipitate out with multiple filter papers. That's because barium sulfate is so fine, it can pass through one filter paper, and if it did, that would lead to an underestimate. The next thing we do is we wash the residue, or wash the precipitate, with water and let that water flush through the filter paper as well. And that's because the solution that was on our residue originally was the fertilizer solution, and that would contain ions. They'd be soluble ions, but when we started to dry it out later on, just like in shipwrecks, corrosion and conservation, when you dry these salty solutions out, they become saturated, supersaturated, and start to crystallize. So we would have crystallized some salts on top of our precipitate, which would have been weighed with our precipitate. That would have given us an overestimate. So we had to wash our precipitate through with water to make sure those ions were gone. The last thing we did, we dried the filter paper and residue to constant mass. So we kept on heating it, drying it, weighing it to make sure it got to constant mass. That's to ensure all water was removed. If we didn't remove all the water, well, that would have given us actually an overestimate rather than an underestimate, because that would have meant our precipitate weighed more. So that should actually be red. So I might highlight that in red so I don't forget that that should have been an overestimate rather than an underestimate. What do we do from there? We did some moles calculations. The moles of precipitate is equal to the moles of the sulfate in the sample we tested, because of the 1-to-1 ratio between sulfate and barium sulfate. We then could calculate the moles of sulfate in the original fertilizer. We could calculate the mass of the sulfate in the original fertilizer. Then we can divide by the mass of the fertilizer and times by 100 or times by a million for parts per million. And the key thing here is divide by the mass of the fertilizer. That's one of the common mistakes, is dividing by the mass of the precipitate. You divide by the mass of the fertilizer. And that's the end of 9.4.3. What's next, or what my plan is next, is to do 9.6.5 and 9.6.6. But as I said before, if you've got any particular requests, please let me know.